Right.
So today we're going to be talking about math.
Yeah.
Woo!
Really?
All right. So 2.1 is linear first order equations. And by nature of being a college student, I'm aware that y'all probably are procrastinating on this stuff. So what I did was I designed this lecture to speed run us through 2.1 and 2.2 to catch us up with the syllabus schedule so that we will not be behind when Dr. Light comes back.
We love you, Kara.
Yeah.
So we're going to start with the definition. It's going to be a first order differential equation. This is differential equation is said to be linear.
Oh, don't give me information yet.
If it is written as y prime plus a function p with respect to x times y is equal to some function that is also with respect to x. And at first order, I'm going to start now abbreviating from the first order differential equation, DE, differential equation that can't be written like this is non-linear. Okay.
Can you clarify what that equation is?
So y prime is a derivative, like so it's dy dx. Plus, so you could write it like this. You could say dy dx plus a function p with respect to x times y equals f. Cool. Yes, and if you ever have a question, just like interrupt me in the middle of me talking, and I will not be offended. Okay, so does everybody? This is very straightforward, right? We're just identifying what we mean when we say we have a linear first order equation. So I'm erasing now.
Are we gonna do this?
You know you're about to lose.
Let's go. Hang on. Let me make my tally sheet.
Come on, fellas.
Oh, snap!
Alright, so
Takes the L.
we say that y prime plus pxy equals f.
Wait, is this also part of the definition?
No, this is the new one
Oh, okay.
because I erased the other one, assuming that you saw me erase the other one. So we say that y prime plus pxy that is homogeneous. Ooh, more pretentious words to use around English majors.
Let's go.
If f is congruent to 0, otherwise it's
Is that equal sign?
so this is a congruency sign, which in higher mathematics is not, it's not the same as equals, but for our purposes, yes. If you want to substitute equals in there, this is a true statement. It's just that at the higher level, we use a congruency for reasons beyond the scope of this course. Otherwise, it's yeah.
You said if f is something.
Yeah.
Oh, so here, quick terminology thing. So if you see this triple bar, that's what we call congruency. So if you had A and T, A congruent to B, that's what you would read that as. Well, congruency is something from algebra.
Isn't that equal?
It's not necessarily, it's kind of like, okay. we have a lot of content to get to, but if you imagine a clock, and so this was 0, 1, 2, 3. Okay, so if you started at 2 and you added 2, you would get 0 because you start here and you move over twice and you get to 0, right? But we know it's not actually 0. What we mean to say is 0 mod 3. Okay, and so we would say that 2 plus 2 is congruent to 0 mod 3, but we know that's not an equal sign, but it implies congruency. So to save time, you don't need to know this for the class.
So yes, but no.
So ignore you? So ignore what you just said?
What is important is that you know that it's homogeneous if it's equal to 0 and non-homogeneous. Otherwise, it's not homogeneous. Okay, and then we need to cover the trivial solution as well. So since y
Recursive sequences.
equals 0 is an obvious solution, and that was hinted out, earlier. I was joking around with Dr. Lang saying y equals 0, y equals 0. It's an obvious solution, and so we call that. So we call that the trivial solution. Okay, so the point of today is we're gonna learn how to find non-trivial solutions. In other words, solutions that are actually interesting and that you actually have to use your brain to solve for. So we're gonna start today off because I know full of a room of engineers, the first thing you want to see is some pure mathematics.
It's what gets me up in the morning. Isn't it?
Wait, says the also.
I'm like, yeah.
Well, like the solution for the whole thing.
Okay, so you go on tours and
So, yeah.
You might be getting to that, but I was wondering what homogeneous.
No, that's all.
So homogeneous is if we set, so this is a homogeneous equation because we've taken our linear first order equation and we set it equal to 0. So any differential equation that's linear, set equal to 0, homogeneous. Yes.
You just defined homogeneous in the definition. I'm so dumb, I'm sorry.
I was going to say something really sarcastic about how the thing I just erased on the board was the definition. It's all right though, because you figured it out.
It's confusing.
So, yeah, it is confusing. Okay,
all these big words.
so
Homogeneous congruency.
it's an equation, and if you remember, solving a differential equation is the same as finding the curve y that when you do differentiate and substitute, this ends up working out, right? Okay, so now we have a mission, right? We're trying to find what's y in terms of any form of homogeneous equations. So this is going to just involve a little bit of relatively basic math, I hope. So do you see how we would get from here to y prime over y equals negative px?
Yeah.
Yeah, and so there is a nice little rigorous justification for why we can do this. It's good to know why we can use this shortcut just once. You don't have to do it on all your exercises, but if you were to isolate the y prime, this is really y dx equals negative pxy, and then we can divide, so we have 1 over y dx equals minus px. But then before we're able to integrate, we put it into the differential form. And so you have okay, so y over y is equal to negative px dx. And so then we end up integrating this. Okay, does that make sense?
Yeah.
Wait.
Yeah, so then what we do is when you say integrate this, please don't be the person who does this, because this is an incorrect mathematical statement, okay? Because you're really saying now dy dx with respect to what now? You haven't defined your differential because you have both differentials on one side. So never drop the integral bar, so don't do that.
What do we do instead?
Oh,
Well, we're
okay.
well, glad you asked, it's almost like I paid you to ask that.
Oh my God, I got money.
Bro.
Wait, he's got a point in here?
Dark.
Y prime over y equals negative x. So what we're going to do is real quick, we're going to define something. We're going to say capital P of x is the antiderivative of negative p. All right, sorry, not negative px, just p. Px.
Okay.
So who here took calculus 1? All hands go up. So we know that p prime of x equals p, right?
Yes.
Yes, sir.
Yeah.
Yes.
Cool. So then when you integrate in this step to get from here to here, we say, well, if we have the natural log of the absolute value of y,
Absolute value.
absolute value, well, actually, so as we were kind of joking about this earlier, in the previous sections, we were assuming y was either positive or negative. In this case, we're solving for general solution, which means no more laziness. You have to account for everything. So it's gotta be absolute value. So when you do your exercises, it's actually wrong if you don't put the absolute value cards there. And then you will lose points. And guess what? Your grade will do.
Lose points. Go up.
Okay.
Negative slope.
Then, since we just defined the antiderivative of p to be capital P, we have the minus. So it's negative capital P x.
Isn't it P prime?
Besides just.
Oh wait, not here.
Why would it-
Just kidding.
Oh, well, we could use any symbol. I mean,
like-
I could have chosen to draw a cat every single time we have this.
Sure then.
Like, why are we just speaking with being the integral p of x dx? Why are we doing this?
Well, because if I was to just integrate this, it's more actually to save space. So the original derivation in free OpenStax textbooks will just leave it with the integral notation, and then it ends up looking like you're doing grad school level math when it's just sloppy. So since the fundamental theorem of calculus is implied knowledge, we really do take advantage of that shortcut in notation all the time. So as a general convention, a capital letter of a function is implied to be the antiderivative of the lowercase.
Okay.
function. We're gonna see that later today. So then the absolute value of y is equal to e to the k, e to the minus x, because I was sad, I forgot to put that there. And then note now that this is going to be, I'll get this right here. So y is equal to c e to the minus p x, but we have to define everything now because we're talking about a general solution. So c is equal to e to the k when y is positive on the interval I, and the negative e to the k when y is negative on I. Yes.
I think I lost you a little bit on the K part. Is K just like the original constant?
Oh yeah, sorry. So basically when you do integrate, you have to have a constant of integration.
Okay, so it's, instead of C, you're putting a K.
I just put a K. I could have put in a rubber ducky, it doesn't really matter.
Absolutely.
But so long as we're defining this constant in this general equation. So here's something important. Do not just circle this and say this is the answer, because that would be wrong. Because the underlying assumption you make here is that you have not defined what C is, and also on what interval. Because you found with certain differential equations, when you are drawing those slope fields, which you've hopefully done that homework, you'll find that there were actually segments where you literally could not draw a slope because it was undefined. Like something where you end up where you're dividing 0, and you're like, well, can't do that, so it's simply just an undefined slope at that point. Which means that a general solution needs to account for the fact that you could have an undefined region. And so this interval I, or it's also commonly written AB. This is going to kind of be implied to be that interval on which everything is continuous, everything's well behaved. You're not going to have to deal with some random discontinuity. Okay. So this, as a collective thing, that's the answer to this Homogeneous first order linear, yes.
And so we can ignore where y is equal to 0 because we know y is equal to c.
Point, okay, so Caleb, what is it? If c is equal to 0, what is y? So this implies y equals 0, and
is
using our
trivial.
wonderful vocabulary.
Trivial.
And so, yes,
We love
really
it.
say, yeah, it's trivial stuff. And nobody cares about it. So,
Because we don't have to include that in our solution.
no, it's implied. So if you do this part, so if you define y and c on the integral, you're good.
Got it.
Yes, Austin?
Yeah, that's what I was gonna ask, so when we write our answer, we have to distinguish what C is, right?
Yes.
It's completely answer.
Because now we have to be precise about what we're talking about. So we were making lots of jokes about curling the C a little bit different and whatnot. That's nice, but then we need to get in the habit of actually naming our constant stuff, because the more times we take derivatives and antiderivatives, and the more things we have to deal with, you're gonna screw yourself over really bad if you don't keep track of everything, and then you'll end up making incorrect mathematical statements at the end of the day.
So on the interval, do we need to find what the interval is, or we just state that, it's just A comma B?
That's a good question. The interval is something that you look at the original function. So when we get to concrete examples, you'll see that sometimes, like if you have a rational function like k over x, well, x can't be 0
Right.
anywhere in either the derivative or the original solution function. So then we would say, okay, I has to be something, so this interval cannot include 0. And so then you would base that off of that.
And then none of that matters when we're doing initial value problems, correct? Because we're only looking at a specific point rather than an interval.
We'll get to initial value problems. It's very, very parallel to the thing we do. Once you get to this step, you look at your initial condition, you say, okay, so did I choose an x value that was positive? And you're identifying the interval of continuity that you chose your initial condition in. And then you choose that specific one. Because sometimes, because we're in big boy math now, unfortunately, you might have like 4 points of discontinuity, right? Or like 4 asymptotes in a curve. Well, if you have an initial value that's in one of the 4, you sure as heck better use that interval that it's in when you actually describe this. Otherwise, you said something completely pointless.
Right.
Okay, so hopefully that makes sense.
So in a sense, the constant that we wind up with in our solution isn't exactly constant. Because depending on what x value you put in, it because it can be either positive or negative.
You bring up a good point when it seems like the constant is a variable.
Right, but not
So,
really.
when it behaves inside of the function, it is strictly a constant.
Right.
When we describe it like this,
Right.
we're recognizing and we're basically painting the bigger picture, and this is why we had the direction fields first.
Right.
It's because that opens your mind to the concept that yes, this is constant for a particular curve, but ultimately, depending on where you are, this constant changes depending on where you fix and anchor yourself in this whole field. So does that make sense?
Yes.
Oh, is that like kind of like the family of curves that he was talking about?
Exactly. This helps you identify which ones are possible and how that would be defined from the problem statement. But then ultimately, it does behave like a constant. It won't behave like a variable.
Just to make sure that I'm kind of getting this. So what we just did right now is, did we just say that if you have a homogeneous function that looks like that, that can also be written like this, which is,
Okay.
or are we, because this isn't like a specific problem, right?
So what we did was we took every single first order linear homogeneous differential equation. We described it as it was defined. And then we said, okay, what's the general solution for all of those? That's what it is.
For all first order homogeneous.
Now, what I would strongly recommend you do, if you memorize this formula and that's it, then you're probably not going to pass the exam.
No.
Because the point is being able to do the derivation for the different combinations of functions you have. So don't memorize this. The reason I come to this point is because it shows that you can indeed find a general solution, because there are like the vast majority of differential equations out there don't. And so that's why a class like this is when you look at it from the pure math perspective, it's kind of like, you're picking and choosing the only things that we know how to solve. And then we're pretending that we know everything else about math. So,
Sounds right.
Round two.
Yes, actually. And I will use that as a exercise to the reader.
Thanks.
Caleb, are you ready?
Come on.
Oh, this is so
One
stressful.
line, which means you're still down like 3.
Whatever.
Okay, so you might, the more curious and people who are paying attention might have realized that y prime plus pxy equals 0. This is only one kind of first order linear, it's the homogeneous one. But what about just a general first order? Right, so what if instead of just the 0, we actually let this be a function with respect to x?
So is that not?
Now, here's where things you actually kind of sort of bring it in a little bit. So definition. When considering
To be clear, this is the non-homogeneous case, right?
yes, we're no longer homogeneous. What do you tell me? Is this homogeneous? Why not?
Because it's not equal to a constant like 0.
That's a 0.
Well, that's why the congruency thing existed, because if it was congruent, because that means you can't just say f is 0, haha, we just trolled the universe. No, so congruency means it's got to be the 0 number. It's got to. That's just like caveat. But yes, you do bring up an excellent point. F of x still is allowed to equal 0, but that's one function out of an infinite number of functions. So when considering a non-homogeneous equation, and then that's y prime plus pxy is f. We call the homogeneous equation so the homogeneous equation is y prime dx y equals 0. We call this, with if we're considering one of these, we call this the complementary equation. This is a super important equation because this is going to help us unlock the strategy that we're going to mainly be discussing today to discuss more difficult first order DEs. Okay, so everybody raise your hands if you have finished handwriting this down. I will wait.
So we're considering a non-homogeneous equation, right? But we're going to consider the homogeneous equation. It's going to be useful later. Okay.
The non-homogeneous form of the equation.
Thank you so
is
much.
something that math builds on itself.
Right.
Is that we actually use the easier thing to then help us solve the harder thing. Y'all are engineers. So you know how to problem solve, right?
Allegedly.
Bold of you to assume.
It's literally
So- Yeah, you're
Break your right.
okay, because I'm gonna put one more down. So question, if I write on
Yes,
this
I
side,
don't
can
have
you actually
answers.
see that or not?
not fun.
Like
you write on this.
So if I write it in this height, can you see this or no?
If I leave,
probably.
I can see everything perfectly.
Well, because you're trying.
Because I'm the most important, obviously.
So let me just erase that and write it.
No, I got it closer so that I could heckle him.
Yeah, I'm sorry I stole your seat.
So we're going
you
to.
feel bad, Chappie. You should feel like a horrible human being.
I
Okay,
do.
raise your hand if you took half one. All hands go up. Okay, so who knows what use substitution is? Who knows what integration by parts? Like these are all what we call these methods to solve problems. So there's a very specific method we have in called very specific method. Method of using a solution of the complementary equation of the complementary equation to obtain solutions of a non-homogeneous, I hate that word, equation is called variation of parameters. Okay. So we're going to talk about the general way you can solve any first order.
Woo.
And it involves using math.
No.
Okay, so do you guys have this written down?
Yeah,
I'll give some of these.
I'm done.
Okay, what's the last one? What's the
Equations.
variation of?
Parameters, sorry, my handwriting is, it's like my hair gets worse every single day. Flatters. I'm turning red, Nate.
Oh, well, you don't grab my stuff, I don't care. Just kidding, just kidding. Just kidding.
He said I take it back.
Variation of parameters.
Right, the whole thing back there.
Caleb.
Come on, guys. Get wrecked.
Oh my god, this is terrible.
Alright, so here's how variation of parameters works. We say if y. Okay, so y is an important letter in DPQ because that means we're talking about a solution now, okay? So y equals u times y1. Let's dissect the anatomy of this equation real quick. U is actually a function, so do not think that u is constant. Okay, so u,
Is this another definition?
not really.
Okay.
It's more just like a procedural thing. So u is a function. And y1 is a solution of the homogeneous equation, or we could call that the complementary equation. Okay. Now, there's a caveat here. It's a solution. So now we don't have to worry about the most general possible solution for y1. That's going to come in handy because later on we're going to take shortcuts that are allowed by the nature of the definition of y1. Okay. So let's actually now, but
That's a Y1, not a comma.
yes, that's what y. So
Okay.
So that u is only based on x, or is it gonna have x's and y's?
it depends on what you're talking about. So that's kind of why I'm going to give an example so that you'll see kind of where everything's coming from.
Is there a then to that sentence? Do you have an if? Or is it just y equals
Oh,
y1?
well, so this, I just took a moment to tell you what these are. I'll answer it. I'll answer it right now.
He said it's there more. Are you gonna finish?
Okay, so if y equals u, so the reason I had to establish that is because I'm gonna ask a question that requires to remember which calculus one is. So
It was a long time ago.
Place.
y prime is equal to y. Okay,
You.
who here took Pug one, raise your hand.
Oh, it's
Beautiful, so
chain
product
rule.
rule.
Oh,
Prime y1 plus u y1 prime.
I knew that.
Yeah.
Yeah. So that's what y prime is. So we're going to substitute this back into the equation that we were originally trying to solve, right? Because this is similar to those exercises at the beginning of the semester when you were verifying if a certain y was a solution of a differential equation. So we're verifying if this is a solution of y prime plus pxy equals f of x. We're verifying this, okay, so y prime plus pxy. What's y prime again? Well, we just computed that, so it's gonna be u prime y1 plus u y1 prime. Now we've got to add plus p of x times y. What was y? It was u times y. This is an equation that we now need to work through. So the first things to note is
So f of x is equal to y prime, not y.
well, this is okay. I should explain this a little bit better. This is the equation. This is a differential equation, and we're trying to show that this is a solution to this. So we're taking the derivative of this and then plugging in the values, and then we're going to eventually make this equal to f at the end. So yes, you're looking, you're 2 steps ahead. We're eventually in the strategy going to set whatever we simplify this down to be equal to f. And then that'll be the crux of the strategy, yes?
So we're using the y equals u times y1 to define p of x. So that
Yeah, we're defining, basically we're making an assumption. We're making the assumption that this is a solution to the differential equation. And then we happen to define it this way. And so after we make this assumption, now we're computing it and then substituting everything back in to see if it checks
All
out.
you've done so far is just substitute y and y prime into
Right.
the non-homogeneous equation.
I love the way.
Okay, and so this, like you were saying, we could put this just equals f of x. And then now what we can see, we have u prime y1 plus, we have a u and a u here, so we might as well factor that out, right? So u, and then we have y1 prime plus px times y1 in there. And that equals f of x. So I have a question for you all. Yes, I'll-
could you explain the part where you got the plus p of x, u y1 again?
Oh, okay. So
That's just one.
what was y prime? We computed that to be this. This is y prime. And so we substituted this y prime, so that was this guy. And now p times y. We're assuming y is what? The very initial assumption from the get-go was that y is equal to u y1. So that's why I say no p times the way we define y is u y1. Good? Okay.
y1
So
prime plus
So I don't need this.
y1,
now,
which is this that, but with y1s.
yes, so Josiah here was paying attention in class. So he recognizes that the equation y1 prime plus pxy1. Oh, we're assuming that this is the solution to the complementary equation. So what's 0 times in?
0.
0. So that means this is just 0. And that 0 times u is 0. So cha-ching, and then we have u prime y1 plus 0. I'll get to you in 1 second here. Equals f of x. Yes.
Wait, why do we, is like, you define that equation equal f of x, why are you not defining that equal to 0? Are we just like putting 0 in as like a substitute per se?
Oh, okay. So the original assumption is that y equals u y1.
Yeah.
Now, we assumed that, remember when I had those other sentences written out, we're assuming that y1 is a solution to the complementary equation, meaning that this y1 has to, by definition, satisfy this exact relationship.
Okay, so okay.
And so then it happens to show up in this fact when we factor out u, slap it in, bam, let's go. Okay, so now ultimately we're trying to figure out what this function u is, because if we can figure out u, then we're all set to go, yes?
So you said that we're assuming that that function with the y1 is the homogeneous function, right? That equals 0. We're making that assumption.
Yes.
How can we make that, I guess? is my question.
Well, it's because we're using variation of parameters. So y1, when you make this guess, the actual theory behind it, you're tapping into a really pure side of differential equations that I would be more than happy to spend 4 hours discussing with you. It's very complicated. Point is, the complementary equation is related to the non-homogeneous equation by a theorem of which the proof is contained in quotes advanced text. So the answer to the question is, I have no idea how to prove that because I am not a grad student.
So we just assume.
So we're making that
Trust it.
assumption. We're using well, we're not trusting. We're using a result of a theorem, which means it's been proved to be true.
Yeah.
And then we're claiming, okay, we're stating that theorem and we're using the theorem in analysis.
And say, how could we do that?
So does that answer your question?
Yeah, thank you.
So then now to isolate u prime, what do we do?
Divide. Someone smarter than me said so.
So f of x divided by y1, and y1, remember, is a function of x. Okay, and so what would we want to find u, but we're giving it derivative?
Integrate.
Wow. U is the integral of f of x over y1 x x. Okay. So we almost forgot.
Plus, okay.
Wait,
Let me do it as a C because C is pretty cool. All right, so now when we look all the way back at what we were originally trying to solve, it was a differential equation with y. So we can substitute what we just found for y back in, right? So we could say
New
y.
page.
So if y is equal to u times y1, we just found u to be this, right? So what's stopping us from just putting that in here? C plus the integral of f over y1 dx.
Oh,
And then times y1. So this right here. And if you really
Plus
want
zero.
to see, you want to see that this is also flipping it back. So this is a general solution. And here's something to note. We're assuming the non-trivial. So this is how we're finding the non-trivial solutions. It's got to be non-trivial because if we were counting the trivial solutions, we would be dividing by 0. So in other words, we would be doing illegal math if we're counting for the trivial solution right now. So this is only when we're not doing trivial solutions. We need all of these functions to be continuous on an interval, because if they're not continuous, well, everything breaks down. We can't make any of these assumptions that we can assume all the time. So it's going to be continuous on an interval, and we're talking about non-trivial. So those are the caveats. Design.
What's like an easy way to recognize trivial again? I feel like I should know this, but
If it's 0.
if it,
So y equals 0 is trivial.
Oh, that's our definition, yeah. Y equals Y1.
so if
Homogeneous,
it breaks
right?
down to 0, because I feel like
So it's like if you're trying to plug in 0 for your
Right.
solution,
So
that would
if
be the
you
trivial
said,
solution.
here's a curve y, and my curve y is just a flat line on the x-axis.
Yeah.
This is trivial.
okay, yeah.
What's another example of trivial?
I'm glad you asked that, because guess what's on your homework? There is a problem that you'll do where you'll find that the trivial solution is actually 1. Because if you were to plug in 1, it would actually give you the same exact, it would be like a super obvious. So I guess we abuse the term trivial a tad bit because this is a semi-rigorous, not at all rigorous differential equations course. And so if you can find just by inspection y equals a constant as and that satisfies the differential equation, we just say that's trivial because you can just look at it and see that that would work, but it's kind of meaningless in terms of use. Chris.
Can you adjust the camera?
Oh yes.
It's the.
Hopefully that's part of it.
Thank you.
Because we started with y is equal to u and y1, but what actually is u and y1? Like, where did this come from?
So u is a function that we had to solve for, but y1 is this is like a more like anchored concept. This is explicitly a solution to the complementary equation. It's not just any y1 that we It's gotta be specifically a solution to the complementary equation.
Well, what you pretty much just said was that it has to be a non-trivial solution of that equation, right?
Yes,
So, okay.
right.
Yeah, my question was, we were finding a solution for non-homogeneous. But we plugged in the homogeneous, we also used the homogeneous equation to help us find.
Exactly, so you're hinting at something, and let's see, it is 3:30, which means we have time to actually solve a problem. And given how well you guys remember calculus 1, this is not gonna take forever.
Like it was yesterday, man. So fresh in my mind.
Products already
Is that last equation worth boxing in?
No, once again, don't memorize that,
It seems.
learn how to derive it in derivation.
I didn't know anyway. Caleb.
But so I was like, yeah, I see the derivative calculator.
Oh, this went 3 in a row.
No, you went 2 in a row.
Oh, yeah.
That's 3 in a row.
No.
You win the first
Okay,
one.
so
I wasn't making
example.
fun of that last night. But I
Well,
was
no,
like,
not the fourth
one.
We don't need to talk about it.
what is that? I think I might have shot.
that. What are we talking about?
Y prime.
Example is a fancy.
Y.
You're a fancy.
Wait, did you get the rest of
X.
this? Is that cotangent?
Yeah, so Y
I'm
prime
so
is
excited
tangent
for
X, Y,
parasites.
X cosecant.
You cosecant.
So, believe it or not, this is not homogeneous.
Riot, riot.
Wait, is that XC?
Cosecant, sorry.
Cosecant.
S.
Oh, okay.
I see,
Who's here has taken trigonometry? Raise your hand. All hands go up.
Actually, I never did.
That's fair. Okay, but if you speak the calculus, you should have seen cosecant. Of course. Okay.
1 over
So,
sine.
but now here's something to note. Are these functions continuous for all x and reals?
No.
Oh, okay, so that's kind of like a problem, right?
No.
Because if when we do find a solution, it's gotta be on a specific interval. So it's gonna be continuous, except, so it's gonna be continuous except at x equals r pi such that r is an integer. Because if you really think about it, cotangent and cosecant, the sign is in the bottom, right? Cotangent is cosine over sine, so sine's in the denominator. And cosecant is 1 over sine, and sine pi, sine 2 pi, sine 3 pi, 0, 0, 0. You can't divide by 0. So that's why we're taking all the integers r times pi.
That's a pi?
Totally too. Next to the R.
Fancy car.
Okay.
Look like a fountain.
Then, so we know, so what we know about so the
R is an integer.
solutions
R is an integer.
are on the intervals. R pi, and then R plus 1, like the next integer over pi. So these will be the intervals of the solution. Since this is not an initial condition, it's not, we don't have an initial condition, we're not going to specify exactly which one this is. So we're solving for the general solution because I wrote down to find the general solution. So now the strategy. How are we going to tackle a problem like this? First thing first, we need to find a y, we need to find a solution of the complementary equation. So let's rewrite this. So the complementary equation is y prime plus cotangent x y equals 0. And since now this is complementary, we're going to put the subscript 1 on these y's. And we're going to find a y1 that does actually satisfy this equation. Yes.
So we're just solving on one side of the equal sign, so that makes it easier.
Well, to answer your previous question, remember we needed a key element to solve. We needed a y1. So what we're doing, step 1 is always going to be, let's find one of these guys. And so we do this by solving the homogeneous version of the equation. So no matter what f was over here, we don't care. We're just going to turn that into a 0 and then look for just the y1.
Well, isn't the y1 the y next to the cotangent, just like last time?
Well, yes, I mean, you preserve the form of the equation. You're just now solving for this for the complementary equation instead of the non-homogeneous.
Oh, okay.
equation. Yes. So, well, I mean, hopefully you can see, well, if we just do y1 prime over y1, that's just going to be equal to negative cotangent x. And then when we end up integrating, we get the natural log of the absolute value of y1 is equal to, oh man, okay, so you either have this memorized or you don't, and I don't have it memorized, but you can derive it very easily. So we're trying to integrate the negative cosine x over sine x dx. So we do a mini baby u step. So u is sine and du is cosine x dx. So this is du and that's u, which means that we really just have the natural log form. So it's going to be negative natural log of the absolute value of sine. Now, here's the thing. And this is good to know. When you're finding the y1, when you're finding the solution to the complementary equation, it could be any solution. We're no longer trying to find a general solution to this. So we could put the constant of integration here, but we could also just set it equal to 0 because we just need any potential curve.
Go
And
waste.
so really, this is actually kind of easy. We just have y1 is equal to 1 over sine x. This is a perfectly acceptable, it's in the family of general solutions, but we just need one explicit solution for our purposes for variation of parameters. So if you put instead something different, like, I don't see why you would waste your time with making it more difficult, but sorry, Bill.
So it's 1 over sine x because negative natural log of sine x is the same
Yes,
as.
I'm sorry, I
Yeah.
assumed high school algebra in this
Right,
step.
right.
And then, what was your question?
That was it.
Okay. So now we have
Pre-K.
y1 and we need a u, so we can finally use this. So ultimately, we see some y equals u y1. I very strongly recommend you write this down in your solutions. After solving for y1, write this down because you might forget what the heck you were doing and then just circle this and that comes down, which you're not. So y equals u y1. And all we gotta do is substitute in. So y currently looks like this, u over sine of x. And now, how are we gonna find u? Well, what we're gonna do is we're going to assume that this actually is the solution and then make it, make it conform to this. So what's y prime?
Why?
Yeah. Here to come one, I'll hand it.
So it's
No, sir.
numerator prime,
Second guess.
so it's u prime sine x
U prime sine x
minus
u
cosine x
over sine squared x. This is a perfect opportunity for me to plug Dr. Ling's beautiful summary of all of the derivative rules, all of the integral rules and all that. Because from here on out, he is going to assume you have the entire 4 pages memorized by heart and you do it all. And so that's just kind of the nature of taking math at college. You have to remember stuff. So this is like prime. Now we can substitute it back into the equation. So actually, let me do it over here. So have y prime plus cotangent x y. Let's substitute what we now have for y prime and y in, because, okay, do you recognize this is in the original question statement right here? Okay. So y prime is u prime sine x minus u cosine x over sine squared x.
Yeah, should we simplify that?
What we're about to, and then plus cotangent, so cosine over sine times u over sine. And then eventually we're gonna set this equal to this, because that's ultimately what it's supposed to equal. And so when you factor out, you see that you're gonna get the same denominator, factor, cancel, cotangent, and then you have u prime over sine x is equal to x cosecant x. And then this implies that u prime is x, right?
So we just, so u and u prime over there, we just plug them back into that, okay?
So cosecant is 1 over what? Right, so we're just canceling those out, so u prime equals x, yes or no?
The cosine x over sine x, is that a multiply by or minus sign on the?
Oh, this is a times.
Okay.
Okay.
So if u prime is equal to x, then u is equal to x squared over 2. Now we do need to include an integration constant in this. And so now we have all the parts we need. We have u, and we have y1, which is over there. So the solution, the general solution, is going to be y equals then x squared over 2 plus c times, and then I'm just going to write that as cosecant because it's nice on one line. And then on the intervals r pi, comma, r plus 1 pi, such that r is an integer. And so this, all of this information collectively is the singular answer. If you are missing any parts of that, then you have an incomplete solution. So that, does anybody have any questions for me? Actually, I would not be surprised with the way Dr. Lang writes exams that it's going to be harder than this.
Oh, yeah.
And that interval was given to you in the question, or how did you find the interval?
Oh, so there was a little bit of intermediate work we did at the beginning here. So it's basically a commentary of is cotangent it's, the word leads me continuous on all x, and then it's not, and so I can take it in between those little chunks.
Sine.
Yeah, I forgot.
Also sine theta.
So on that line where you plugged in y and y prime, that is all equal to cosecant x cosecant x, right? But is that just not written? in the
Oh,
next line?
so I did this in my head.
Oh, okay, so where's cosecant? That's coming
So,
from,
oh, I see what you're saying. So
right,
basically, this is disgusting, and so then you reduce it down to here.
right,
But then ultimately, we set this and this are the same, and equals this, equals this. So it's just putting that at the end of the equation after reducing the other stuff. Right?
For your interval, on the right
I
side,
like
the
it.
all real numbers representing the y. I'm a bit confused on what the
Oh,
intervals
okay,
actually
so, can you divide by 0? Okay, so cosecant is 1 over sine x. So we break continuity whenever we find solutions where sine x equals 0. So when sine x equals 0, this occurs when x is equal to r pi, where r is an integer. So like plug in 1 pi into sine. What do you get? Sine of pi.
either 1 or 0.
That means 0.
You
Now
just,
what sine of 2 pi?
you just took it from the denominator, you
Sine
took
of
the
17 pi.
u over sine x,
So if it's an integer times pi, you'll get 0.
and you put the sine x,
So
turn the
for
sine x
all
into
of
the
these
cosecant
equations,
x.
we break the continuity space.
Oh, okay.
So that's why we have to be in
And plug in u.
between.
Is that what you're asking?
Yeah. Because I was like, how do we select x? Because it's like we multiply by sine of x.
Oh, I think you might be thinking of range versus domain. The actual range of this equation,
Should be all in the numbers.
I have no idea. I'd have to work that out.
I was just wondering, I only saw the x interval.
Okay, so as long as you know what homework, you guys know what the homework is due, right?
Monday.
Which things? Which-
2.1, 2.2.
Thank you, Friday, Monday. All right, well, then now class is officially dismissed, you can go.
That was all,
Continue procrastinating.
that was all 2.1,
Continue
right?
procrastinating. You have so much good.
This was 2.1. It's, when you read 2.2, you'll find that it's actually really similar. Like, it's actually not super math, it just uses a little bit of terminology. That describes one more kind of equation you can manipulate out. Messiah, yes.
Okay, I just have a couple questions.